Firewall that we developed.
Would you mind announcing that we're taking down the VM? We're taking down the servers. No more server access.
Okay, we are taking down the VMs now. So if you still the servers, so we're loading other stuff. So sorry. Yes. So if things stop working, then there's a reason. You can still use the VMs, but just the servers with the NFPs in won't be working anymore. Okay, so I'm based in Centurion in South Africa, and I'll be showing you the Stateful Firewall that we developed using the Netronome software development kit, the one you're getting access to today. So just to get everybody on the same page, I will quickly give you an overview of the firewall and the network address translation. Then I will show you the specific setup we have for the demo today, as well as a sequence diagram just to show you what happens to the packet at which time during the process. Then I will be showing you just what we are actually demoing. We are using the firewall as an example, but we are actually demonstrating the functionality that you have using the software development kit. And then after I do the demo, I will do the code walkthrough just so that you can have more idea what's going on before you just see a bunch of code. So a firewall is there to protect one network from another network. So you typically have an internal network connected to an external network, and you don't want traffic to come in from the external network into your internal network without allowing it. So different types of firewalls. You have a software firewall, usually in your operating system, the one giving you the annoying pop-ups, which you just have to cancel all the time. And then you also get the hardware firewall, which is actually on a network hardware device. So the one we're demonstrating today is developed in P4, so it's software, but it takes the role of a hardware firewall. Different approaches to firewalls are just a default allow, so everything goes unless you specifically block it from going through, and a default deny, which is the one we're going for, where everything is blocked unless it is specifically allowed to go through. In more specific, we have an internal side and an external side. So everything from the external side is blocked by default unless a request is made from the inside, which will then add rules like you did, but this will be dynamically added rules so that the device on the external network is allowed to just make a response, and from there on traffic can flow between the two devices. So network address translation is the process of modifying IP headers in order to forward a packet. So when you have an internal network with private IPs, you don't want to expose that IP to an external network on the internet. So the network address translation will then take the IP address and the port from the internal request going out and change that to a public IP of the router and the port going out. So the external device is communicating with the router's IP and the router's port, and the router will then swap that back to your internal device, staying safe behind the firewall. So different types of NAT is full cone NAT, restricted cone NAT, port restricted NAT cone. There's a lot of information about this, but the one we'll focus on today, which we implemented, is the port restricted cone NAT, which means the IP address and the port are mapped to the external IP going out. So when that external host gives a reply back to the device from the inside, it must be exactly the source IP and the source port going out must be the destination IP and the destination port for the reply coming back. So as far as the P4 program goes, we have 4 tables. We have one table specifying when a packet must go to a controller to be able to add the rules, when it's coming from the controller, and then the one we'll be focusing most on is the NAT table. We will actually do the network address translation, and then we also added a payload scan. We are calling a C function from within P4 to scan through the payload, and we're using the example of just searching for a $, and then In this instance, we're just counting it, but then you can drop it or do whatever you would like to with that. So the NAT table has 4 actions. We have an internal to external miss, which means this is the first time the internal device is making a request to the external side. External to internal. That is the default rule. If it doesn't hit any rule in the table, we are just dropping it. That's the safest way to go. Then we have the internal to external miss, which means we don't have a rule specifying that this packet is allowed to go out. So that will add rules first. These rules will then allow the packet to go out and allow that specific host on the outside to reply again. And once these rules are added, we will have our 2 hit actions, and this will then allow traffic flow. So like I said, from the internal to the external hit means we already have a rule. There was already a request going out. This will then take the source IP and change that to the router's public IP. And it will take the source port and change that to the router's public, or to a port going out starting at 1025. So every packet going out after that will have a 1026, 1027, just to have a different port going out. Just the opposite is happening when we get a return, but now the destination IP is sent to the router's public IP. So that is being changed to the IP of the device that made the original request, and the destination port is sent to that port that was selected by the router the previous time, but that is then changed to the port of the device that made the original request. So the test setup we have is our internal network with a number of devices on the inside. We have our firewall. This is a server containing a NFP. In this instance, we have a lithium. The lithium card has 2 ports. And we have our controller. This is just a Python script running on the server, which has the NFP installed in. And the server will be responsible to adding the rules. And then traffic flow will only be allowed once the rules are added. So to put this more in perspective, we're going through a sequence diagram, just showing what's happening. So initially, anything coming from any external host will just be dropped. When one of the devices on the inside makes a request to the outside, it will send the first packet, and the firewall will detect that there's no rule to allow this yet. Because we're using TCP traffic, we want to hold on to that packet, so we can't just drop it. We have to send that packet to the controller. While the controller holds on to that packet, it sends 3 rules. So the first rule is to allow the next time this device makes a request to that specific external device, that will allow it to go through, so it doesn't have to go to the controller again. The second rule will allow this packet coming back from the controller to go out. And then the third rule will say that if this specific controller or the specific external device makes a reply to the inside again, that must be allowed back. If it sends to any other device or any other IP on the inside, it will be dropped again. If any other host on the external side tries to send into any internal device, it will also be dropped. So this 3 rules only specifies between these 2 specific devices. Now, if you just get requests on and on and on, then this list is just going to grow. So we decided just to add a timeout. So if no traffic, if none of these rules was hit, within a certain time, we're polling the counters for every time a rule was hit. Then those rules just gets deleted again by the controller. So typically, the middle rule just adding from the controller will quickly be deleted because that packet just comes back once from the controller and goes out. So it will only hit once, and the first time the polling happens, that rule will be deleted. So the other 2 rules remaining will then only be deleted if there's no traffic between those 2 devices for a certain time. And then after the rules was deleted, the external side will be just blocked again. And if the internal device makes a request again, it will have to go through the whole process of adding rules again, using a different external port this time. So what we are demonstrating with this is multiple match types in a single rule. So in order to do this, we have exact matches, ternary matches, and we're checking for valid TCP and valid IPv4 packets. And we're doing the 5-tuple matching to do the address translation from the source and destination IPs and the source and destination ports, as well as the valid protocols. Since we're using ternary, it's a possibility that you can have two rules being hit at the same time. And for that, you need a priority to decide which action will then be executed. So I will get more into depth when we go to the code. But basically, in our NAT table, we have two initial rules. One is the default rule saying the job, and the other one is a ternary match, which matches on any IP, but with a very low priority. So when you get a ternary match again, the dynamically added rules will have a higher priority. So those rules will be then hit from then on. We're also adding custom headers, adding and removing. So when we send the packet to the controller, we want the controller to be able to identify this packet as valid. Otherwise, the controller will just ignore any other packet it receives. And when it sends the packet back again, that header must be removed again in order to send a valid packet out to the next device. We are also defining a primitive action in C, in P4, so that we can execute a cease function that we will search for the $sign in. Since we are modifying header data and changing the IPs and the ports, we have to recalculate the checksum before we send the packet out. And we're also using counters and then the Python controller, and using the runtime API, we will dynamically add rules and remove rules using the Python controller. And if we have time, we will just go through setting breakpoints and stepping through some of the code. This is, like I said, just a demo, but we can keep it interactive. If you have any questions, please feel free to ask. And if I'm not able to answer, I'm sure one of my colleagues will definitely be able to answer your questions. The source of the timeout. We just have a timer in a Python script, and then that just creates a new thread just to. Yes. Okay, so by this time you're probably familiar with the IDE environment. So we created a new project like you did previously, created the files, built them, and I already did the start debugging, which you saw the loading microcode takes quite a while. So now I'm at the step where you will start running the program. So now the program is running on the NFP, the lithium. It has two ports connected to a different simple NIC, also to two ports. So we have two ports connected to each other. The one port in the place of the internal network, and the other port representing the external network. So to represent that, we have our terminals here. The one at the top, I'm not sure if you can read the title, but this represents the internal side. So this will be your phone or your laptop on your local area network, and this one at the bottom is the external, some server on the internet. In this terminal, we are running our controller. I set the timer just to a very long time, just so I can demo this, but the time can be set as a parameter. And then in this terminal, we are going to send the packets. So first, to illustrate, I will be sending a packet from the external network to the internal network. So what we expect is that the external side picks up this packet, But because there's no rule, it's from the external side, it just gets dropped, so it doesn't go through to the internal side. Now, to enable traffic from that external host to the internal device, we have to send the packet out first. So this packet will be sent to the inside. This will pick up that it will hit that initial rule matching on any IP. It won't hit the default rule because it comes from a port that we set up as an internal port. In our rules, we say this is an internal port and this is an external port. So it will see it comes from the internal port, but it doesn't have a specific IP that says, okay, you can go through. It will just hit the general rule with a low priority, and this will cause it to be sent to the controller. So the controller gets it, and the controller adds the rules, and you can see it goes out to the external side. So now we have rules specifying that we don't have to go to the controller again, and anything from the outside, from that specific host to which we made the request, can then reply to the specific one on the inside. So sending in again, you can see it came up on both the inside and the outside, and sending out again will also be. So we're not hitting the controller anymore because those rules are added. Now, since this is only between these two devices, sending a different packet from a different device will still be dropped. So on the external side, you see that it came there, but it didn't go through to the inside because there's no rules and it's just a drop. Now, to see the rules that was added, you can go back to Programmer Studio and stop running. This will then update, retrieving all the rules currently in the runtime environment. So going to the rules, you will see, I actually should have shown you before, it was just the default rule and the one matching on any IP. So our ternary match is a zero mask with a zero value, so any IP will match this. Now the newly added rule will have a mask of all ones with a specific IP on this one. So the next packet coming from this IP will both hit this one as well as this one, because this is any IP. But because we have a priority set higher, it will rather execute this, the action defined in this rule. Where this rule said it's a NAT into X miss, which means send to the controller port. This one then says it's a NAT internal to external hit, which means sent out to the external port. Another thing I didn't mention is that the controller, because it's running on the server, it's connected via a virtual function. So it is seen as a port, so it just, as far as the program is concerned, it just sends it out a port, but it's not a physical port, it's a VF, and in this case it's VF 0.1. And then the external one is on P1. Is there a question? Oh, sorry. Okay, so to enable communication between the other device as well, we can just send out to that one again. So it goes again to the controller, and it should send it out. Oh, thank you. That's a common mistake, forgetting to start running it again. So because this packet was already sent and I'm only clicking run now, it should pick it up, and there it sent it out. Okay, just to demonstrate the timeouts, I'm just going to stop the controller again and give it just a short 3-second timeout. Just before that, I would like to show you the new rules was now again added. So now we have 6 rules. Because the timeouts didn't run, we still have the controller rules, but this will be deleted very, very quickly, and then just the others will stay there. So running this with a quick timeout. We are actually, every time a rule gets hit, it increments a time counter, and then we reset that counter again. So when the timeout runs again, we see if the counter is 0 again, the rule wasn't hit in the meantime, so we can go ahead and delete it, and now all the rules are deleted. Okay, so stopping, I didn't run it. So running the code only is needed when you send the packets. The rules can be deleted without the program running. So as you can see, we are set back to the initial setup with our default drop rule and our initial rules telling the packet to go to the controller. Any questions thus far? Any? Yes. The NAT is just plain P4 functions, yeah. We are not doing any primitive actions there. Okay, so to take you through the code of achieving this, I just arranged it a bit more to put my parser functions in a different file and the headers in a different file, and the firewall where all the action actually happens in a different file. So the headers are standard. This is mostly copied and pasted because IPv4 will stay IPv4. The one I would like to put your attention on is the controller header, which is a custom header we defined. We are just adding a reason, like I said, when the packet goes to the controller reads this header. And if it's not set, we are just setting it to 1 at this stage. But if it's not set to 1, then it just ignores that one. So if it's set to 1, it knows it comes from this, and it must continue with the adding of rules process. And then because we now only have one internal port, but if you have multiple internal ports, you can also remember which port this initial request came from. So if you get a reply from the external side, you can send it out that specific port where the request came from. And then we just have a filler of 32 bits, because in our parser function, this actually leads me into the parser function, we look for, if the first 48 bits is set to 0, we know that this is not a valid packet just coming from somewhere with a MAC. It's set to 0, so we have to parse the header, the custom header first. Otherwise, if this is not set to 0, then we can just continue to parse Ethernet. I'm not sure if you have seen a select statement yet. It's similar to a switch statement. We have case 0 and then the default, just to say what would be the next step in the parsing. So if it came back from the controller, we are parsing the controller header. Otherwise, we're parsing the Ethernet header, parsing IPv4, and then parsing the TCP. Now the NAT table, as you've seen in the rules function, we have all of these match types. So we are just looking for the ingress port. Our rules specify that P0 is our internal side. We have to have a valid IPv4 and a valid TCP. And we are looking at the source destination address and the source and destination port, all on ternary matching to enable that priority that I showed earlier. Now, in P4, I believe all of these matches is an AND. So all of them must match in order for this table to be hit and to make this one of these actions happen. And in the rules section, for every one of those, every rule, you specify which action to take if this rule gets a hit. So the options of actions to take is the internal to external hit, external to internal hit, and then the misses. Now, if you have a miss, like I said multiple times on the external side, you just call the basic function drop, and the packet will just be dropped. if you have internal to external miss, so there's no rules allowing it to go through yet, we are only modifying the standard metadata egress spec. So this changes the port that it will be sent out, and in this case we are changing it to the VF connected to the controller. So the controller is just listening using Scapy, a Python function, just to listen on a specific port, and it's set up to listen on this virtual function. Important to note that you can only set egress spec in the ingress control. I don't know if you've noticed in the previous lab session, you have egress control where you apply some of your tables, and you also have ingress control where you apply of your tables. So that egress spec can only be set in the ingress control, otherwise it won't have any effect on the packet going out. So it will go out on the port selected at the end of the ingress control section of P4. Now if you get a hit, we are actually doing the network address translation. So in the event of going out, we are changing the source port and the source address. And in the event of receiving a packet back, we are changing the destination address and the destination port. Now, where we get this parameters from is when we send the packet to the controller extracts the destination address and the destination port. Actually, it extracts the source address and the source port because it's a packet going back, but it adds it to the rule allowing it back, and now it's being added as a destination because that external device must reply to those specific set of IP and port number. And then we are also just changing the egress spec. So we already set it up which one is the external port. So we're setting that also here. So that is the network address translation function. Now to do checksum recalculation, you have three things you have to add to your P4 code. Is your field list. Can you? You have a field list where you have all the fields that it must use in the checksum calculation. You have a function called field list calculation where you specify the algorithm it must use to do the calculation. And you say when it must verify the checksum, and it must also, I think it happens when you do the update IPv checksum. It takes these fields and then use this algorithm to recalculate it. So if you have this for IPv4 and you have it for TCP, for the TCP side, then the packet going out. Before we added this, in the TCP dump window, it actually showed checksum incorrect, but if you add that code, it's automatically, you don't call that from anywhere within the P4, it gets automatically called or something, but that actually recalculates the checksum, and if you look at the TCP dump and you have all the right parameters, it will show the correct checksum. Now for the counter are just defined like this. So in a counter you can either count the bytes or you can count the packets. In this case we only want to know was the rule hit or wasn't it hit. So if it was hit, the counter just increment once because it received one packet. And every time on that pole the counter is reset again. So we know if we have a 0 again, then this counter didn't increment and we can delete that rule. And the direct means we are counting every hit on the NAT table. So it will create a separate counter for every rule in your NAT table, and it will count every time that was hit. For the primitive action doing let me just start running so long. I believe in the previous lab you did do add headers and remove headers. so you did see that. So you just do, in order to call a C function from P4, you have to specify a primitive action with the name of the C function you would like to call. Then you just set up a normal table like usually, and it reads on whatever fields you would like to match on and whatever match types you would like. The match types are exact matches, you have range matches, ternary and long LPM, as well as valid. So that's the match types you can have in P4. And you specify action. In this case, we just have the one action, because every packet that comes in on the external side, we want to just take a look at the payload, and then we want to do the C function for that. So we just have to make sure it's running still. Okay, still loading the microcode. So as far as the C code is concerned, I'm going to talk myself into a corner because I didn't develop this myself. But we are basically just defining a variable that we keep the counters every time a $ was detected in the payload. We increment a value that is stored in a variable. And then for the demonstration, we are just reading that variable and showing what its number is. So I'm just sending just have to start the controller again. And allow traffic to go in and out. So I'm just going to send the packet out again. Going to the controller, being sent back again. Where's the mouse? Oh. Okay, so we sent one packet in, which contains, in the payload, contains a $, and you can see the variable we declared in the C code has incremented by 1. Sending that again will be 2, etc. So any other packet being sent which doesn't have a $ in won't increment that. And it will just be incremented by 1 again because I'm sending it again. So any questions? Yeah. Sorry? We will make it available, I think. Any piece of code you would like me to just explain a bit more or go through? Yes.
I just have a comment. I mean, the modify field thing is just embarrassing. Hopefully they realize that that's an assignment statement and fixed it in the newer versions of before.
Okay.
Because it's just a lot of pointless typing.
Yeah.
You don't need it. It's better to look like C than look like assembly language.
Yes, that makes a lot of sense. Yes.
Yeah, it's really obvious looking at the code.
Okay.
They sort of did that.
Yes.
Are we able to call several functions? Are we able to call skin, right?
Yes. You mean in the same time? I actually haven't done that, but I'm not sure if somebody else knows. The question is, can you call several C functions in one action? You probably can, because the action specifies calling this function, and you have the primitive action, so you will just have another primitive action and then calling that in the same action. So that should work.
Go back through where I extract the previously mapped address translation, so I can pull it out of the table and
We extract it in the Python. I can show you the.
In here. I'm pulling that out of the table, right?
No, I'm not sure I'm following you, but the.
I'm looking for the hit. The external hit that matches the previously translated address, but I need to look up the old addresses that I stored in the table, right?
Yes.
So can you just walk back through that? Where does that come from?
Okay, so you have your action. You want to know where this source address and where this source port comes from.
Yeah.
That is added in the tables. You just stop it here. And the latest packet I sent did add these rules. So when adding rules, you can do it manually. You will add IP address here and a mask value, and you'll say valid and the ingress port. So the controller actually extracted this IP address from the packet it received. And instead of manually adding 10.0.0.1, the controller added the 10.0.0.1. And in order to remember to do the translation back again, it is put at the bottom table here. So the values in here will be sent to the parameters in the action. So the top table is the rules to match on, and the bottom table is the parameters that will be sent to the action.
And when it comes back the other direction, how does that get pulled out of the table and passed into my phone?
Well, you have different rules for that.
Yeah.
So the outgoing one matches on the 10.1 and sends the IP of the router or the going out, and the one coming back matches on with the destination address on the one that was sent out and sends the original one out. So that makes sense.
Can you show the corresponding P4 code where it gets the data from the action parameters and then passes it to the function for translation? Can you show that? Yeah. No, on P4, right? Okay. Where do you kind of pull the information from the action parameters?
With a
Once you hit the kind of
It's in the formal parameters of the keyboard function. That's what they're tracking.
yeah.
Okay, can you show the action function of external to internal gate?
The action?
External to internal gate, can you show the action function?
The action function, okay.
External to internal.
X to int it, yes.
Okay, got it, yeah.
Okay.
So whatever the arguments are there for that port destination address, they are really the action parameters inside the kind of it for that entry, right?
Yes, yes. So the destination address is being changed to the IP address and the port of the inside internal device. And this port is just, like I said, to remember where the initial request came from. Yes.
So in this example, is it fair to say that the P4 program on this is just basically hunting to a Python daemon
Yes.
to determine what the right thing to do should be?
Yes.
Right. So, is there an alternate way of doing that in P4 where the programming of the tables, the management of the table entries, and mapping to actions is done from within the P4?
We actually wanted to do that, but as far as I know, it's not possible to add rules directly from P4.
What about C callout?
I've asked my colleague, he said you can't do that. I'm not sure why, but yeah, that would make sense to be able to do that. But I'm not sure, I don't think you can. We have on the server running a runtime environment, which is our API, and that knows how to add rules to the program. So the Python program just talks to the runtime API, and that can add the rules. And I'm not sure if you can get access to that runtime environment from within C, because then you're already on the hardware. How much you bet that you may know? Okay. Anything else? There's a question? Okay. Should have it open still. Not opening. Okay, there it goes. Okay, can you see there? This is the code. Okay, so we have our main function. We're calling the sniff function from Scapy, and this will process each packet coming in by creating a new thread. So this function will then look at that. We added a reason in our custom header. So that reason we decided we are going to make that 1. So it looks for if we have a 1 year, we can continue to process the packet. Otherwise, we just ignore it. When the controller sends it out again, by sending the packet, it hears it again. So just before that, we make that a 0 again. So when it hears the outgoing one, it doesn't process that again. So it's just taking the port it came from. All of these information are now being extracted in order to put that in the rules that it sends, that it uses to add new rules. So it takes the IP header and the IPs and the ports. It decides on sending out which port we are using now, 1025, and increment it every time. This is a part where we actually add the rules. So you give it a rule name every time, you give it a table ID, and the actual parameters that should be inside the rule. So this is the 3 rules. And then you just change that header back to a 0 so you don't process it again, and sends the packet back. So when it comes back, the first 48 bits will be zeros, and it knows to remove the custom header first. And the timeouts are also doing here. So we are just looking at reading a counter. We have, in our runtime environment, we have a function to read counter values. So all of the counters there are, we're looking at how many rules there are, so we know how many counters. So we read the value of all those counters, and if there are 0 since the last time, then we go ahead and delete the rule. That's basically it. Okay, thank you very much.